Okay, welcome to lesson 20. We're going to talk about the central limit theorem, which is a huge theorem that we use in statistics. It's super handy. We're just going to talk about how we use it. So for here, inferential statistics uses information from our sample to make conclusions, to estimate or test a characteristic from the population of interest. So the idea is I have a question about the population, and in order to attempt to answer it, I take a smaller sample, usually smaller, and use information I see in that sample to try and make a statement about the population. So I start off with my population. I have a question. So theta is generic. A lot of the times we'll be asking specifically what is mu. So we'll take a random sample from that population, and from that sample we're going to calculate a sample mean. So a lot of times this is going to be x bar. And then we're going to make an inference back to the population. So I have a question, what is the average tuition cost of all OSU students? So I take a random sample from all OSU students, calculate the average in that sample, and then I use that to make an estimation or a statement about the average for the population. Really, really important. It really doesn't work if you don't have a representative sample. It's really important to do random sampling here. If you don't do random sampling here, you don't get to do inference here. It's really rough. So how good is the sampled statistic at estimating the population parameters? So we're going to start off, how good is x bar from a sample at estimating the mean for a population? It's going to depend on a few things. So it's going to depend largely like how did we collect the data, so where did the sample come from? We're going to need to know or have some idea how much samples vary from sample to sample. If you're likely to get very drastically different sample means every time you take a sample, that's really, really important to know. And then how big is our sample size? Usually, we really like to have bigger sample sizes. Small sample sizes tend to make us sad. So where we're going to start? We're going to start here. We have a population distribution. Here's a histogram of it. In this particular population, it has a mean, so this is mu, of 50, and a standard deviation of 10. So this is my population standard deviation. So what I can do now is say, hey, you know what, if I wanted to estimate that mean, which we happen to know what it is this time, I can take a random sample. So here, if I take a random sample from that population, so I took a random sample of 10, and I put them in a histogram. It doesn't look identical to this population, but you can see, okay, I have a mean, so x bar, and a standard deviation. And the mean, 43.03, I mean, compared to 50, it's not drastically different there. And then I can repeat this. Okay, I took a random sample of 10. Let me take another random sample of 10. So here is random sample 2. So if you look at random sample 2, now the mean that I got from this sample was 53.57. And I can repeat this, take another sample of 10. And this time my sample means 55.63. And I can just keep on repeating. I can do this over and over and over again. So x bar here is 53.29. And the idea is I can repeat this and get an idea of, from sample to sample, how much does x bar fluctuate? Like how much is it changing? So every time I take a new random sample, I have the potential to get a new value for x bar. In fact, it's likely I'll get a different value for x bar. So talking about these, you start off with your question, what is theta? most of the time we're going to ask specifically what is mu. Except for week 10, we're going to ask about p. So we'll take a random sample, then calculate. It's usually going to be x bar for us, so our theta hat. And then repeat. I'm going to take many random samples. So here it shows 3. And then I'm going to take all of these and we're going to plot them. So there are 3, but then I can keep taking more random samples. And then when I take many random samples, I get this very lovely normal shape. So the idea here is we have a probability distribution of a statistic. So I can have a probability distribution of x bar. So sampling distribution of x bar is what we're getting at least for the next few weeks. And it's the idea of if I were to repeatedly take samples from the population and calculate the sample mean from each of them, and then plot just the sample mean from all of the samples, that's my sampling distribution of x bar. It shows me, hey, where's the sample mean on average? How spread out is it? That kind of idea. So not only that, is we can get an idea, like we know roughly where it should be centered, which is at the mean, and we know roughly where it should be spread, or we can calculate that. We really are big fans of, so x bar is an unbiased statistic for mu, which means that on average, if I were to repeatedly sample, that the sample mean is an accurate predictor for mu. P hat is an unbiased for p. S squared is unbiased for sigma squared. We really like that. So the on average, that means that p hat really helps estimate p well. X bar really helps estimate mu well on average. So talking about these sampling distributions, so I'm going to start with 2 here. This is my population distribution. So all of the individuals in a population, and we have a mean and we have a standard deviation here. So mean of 50, standard deviation of 10. So then here, the idea is the sampling distribution of x bar, when n is equal to 10, that's me taking every single unique sample of 10 I possibly can from this population. So I take every unique sample of 10, calculate the sample mean, and then plot just the sample mean from all of those. So if there were, I'm making this up, 100 different samples of size 10 that I could get, I would have 100 sample means that I would be plotting, that kind of idea. In reality, there's probably a lot more here, but so things that I know, we know that where the sampling distribution of x bar is centered exactly where the population is centered, which is really great. And then we know the rough standard deviation, it's approximately equal to sigma over square root of n. So the idea is how big your sample is does affect how spread out this sampling distribution gets. So really small scale example. It helped me anyway. I have a room, 7 people in it, and they have the following ages. And if you read their ages, you can see I was very lazy. 2, 4, 6, 8, 10, 12, 14. So I'm going to consider these 7 people our population. So obviously it's not a very big population. Maybe it's a family, I don't know. So I can calculate what does the population mean. So if I want to calculate that, mu is the notation I should use. So mu is equal to And I want to basically find the average of these 7. So I'm going to take 2 plus 4 plus 6 plus 8. So I'm going to put a dot 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 in here. Plus 14. Oops. And divide by 7. And when I do this, definitely feel free to check the numbers here. I should get 8. And if you think about it, 8 is smack in the middle. So there's 8. These are both 2 away. These are both 4 away. These are both 6 away. It's perfectly symmetric that way. So my mean, it's 8 years old. So now that I have those 7 people and I know what the average is for those 7. Okay, so now that we have mapped out what our population is and what the average for that population is, I'm going to go ahead and I'm going to take a random sample. I'm just going to randomly select 3 of the people from that population of 7. So here, fill in. Okay, so I got the 6-year-old, the 8-year-old, and the 10-year-old. So what is the mean for this particular sample? So sample 1. So x bar is going to be equal to, so I'm just taking the average of these 3. So 6 plus 8 plus 10 over 3, because there are 3 of them. I should get something like, 24 over 3. That's just going to be 8. So my average in this particular sample is 8 years old. Another random sample of 3. So this time I got the 2-year-old, the 14-year-old, and the 12-year-old. So I can calculate the sample mean for these 3. So I'm going to average these 3. So all the ages added together, divided by the number of them, there are 3 of them. So I'm going to get, let me see, 16, 28, 28 divided by 3. So 9.333. So what I'm getting at is I have gone ahead, I've repeated this process 3 times. I've taken a random sample of 3 people, and I've done it 3 times. If I were to do this and take every single unique sample of 3 that I could list them all, and I could find the average for all of them. So I'm going to show you what I mean here. So obviously overwhelming, don't mean to make y'all hand calculate this, but here are all the unique samples I could get. So here, that's where I take the 2-year-old, the 4-year-old, and the 6-year-old. The average age is 4. And for the second one, hey, the 2-year-old, the 4-year-old, and the 8-year-old. And the average is 4.66. And so on. And I take all of the unique, regardless of order here, possible combinations I can get, and the averages. So now I'm going to just take just those means, and I'm going to put them into a dot plot. So I'm going to look at them. So here, there's a dot that represents every single one of those means. So when I do that, things to note, hey, look at where this is centered. This is nice and symmetric, and it's centered right here at 8. It's actually centered at the mean of the population. So if I took all 7 children together, remember that average was 8 years old. If I take, this is the sampling distribution of x bar. Sorry, of x bar. It's centered in the same place. So here's an example, another way to think about it. You have a couple of researchers. They're interested in the average tree girth in a particular stand of trees. So the first researcher, they go out there and they measure a random sample of 10 trees. So they randomly select 10 trees and then they go ahead and measure the girth on those trees. Researcher 2, it's like, okay, I'm going to answer the same question, but they go out and they take a random sample of 1,000 trees. So one thing to think about is which sample is more likely to give us a better estimate. So like if you had to think about it, a sample of 10, if you have an oddball tree, it's really going to throw your average off, right? But if you have a very large sample size, an oddball tree here or there is not going to make that much of an impact on our mean. So it might work out better that way. Okay, so we have this great thing that we use called the law of large numbers, and what it says is as our sample size gets closer and closer to the population size, that the sample statistic gets closer and closer consistently to the population parameter. That is, my sample mean is going to be more consistently like close to mu. It's going to get closer and closer on average. So if I were to take, a sample of 10 and take the sample mean, on average, it's however close it is to the mean. But if I were to take random samples of 1,000,000, the sample means from those samples would consistently be closer to the true mean of the population. Okay, so just because you have a larger sample size doesn't guarantee that your sample mean is going to be closer. There's some fluctuation. There's some variability. So from sample to sample, sometimes this particular sample is going to be high or be low. It's not a guarantee. You can see here, it kind of levels out and gets closer and closer to that true mean. But it's not guaranteed to always be right at that true mean. So here, as our sample size gets higher and higher, and closer to the population size, the variability of the sampling distribution decreases. The idea is if I'm taking samples of size 10, from sample to sample, the sample mean fluctuates a certain amount. But if I start taking samples of 100 instead, the sample mean doesn't fluctuate as much when I'm taking a bigger sample. That's the idea, is from sample to sample, the average is going to be much more stable. So the variability of the sampling distribution, we call this the standard error, and we either denote it like SE of theta hat or S of theta, so sigma of theta. So then when we're talking about the variability, so how much does like X bar vary from sample to sample, we call this the standard error. So we'll use SE or sigma. So for the next couple weeks, we'll use like sigma of X bar. We also use sigma of, or SE of X bar. So what this is saying here is as our sample size gets closer and closer to the population size, the variability is going to go to zero. It's going to get smaller and smaller. So our sampling distribution is going to get narrower and narrower the bigger our sample sizes get. One way to think about it is if, like I had that children's ages example, if I took a sample of size 7 from that population of 7, I'm going to get an average of 8 every single time. There's no variability. That's what it's getting at. So here, we're going to start, we really, really like this example as our population. We have a population that has an average of 50 and a standard deviation of 10. And then as we increase our sample size, the variability of the sampling distribution of X bar is going to decrease. It's going to get narrower. So for example, here is if I were to take all the unique samples of 10 from that population and take the sample means from all of them and plot them, here's a sampling distribution I could get. if I were to increase that, so now I'm taking samples of 30. So take all unique samples of 30. You can look, they're both centered at 50. They should be. But this one has gotten a little bit narrower. And so if I keep increasing my sample size, so now I'm going to have samples of 100, so all the unique samples of 100, centered at 50, but this one's even narrower. And then I increase it anymore, sample of 10,000, it's really, really narrow there. In fact, there's no variability. Standard deviation is 0. So we have 3 distributions we like to talk about when we're doing inference. So the first one is the population distribution. So this is all of the observations in the population you can possibly get. Most of the time it's not accessible to us. You usually have to take a smaller sample. So for here, you use capital N to denote how big your population is. Mu, it's going to be the center of our population, and sigma, that's going to be our standard deviation for that population. So all of these values are population parameters. So then what we usually have access to is, okay, I'm going to take a random sample of 10, and so lowercase n is equal to 10. I have S is equal to 9.7, X bars 52.7. These are values we calculated from a particular sample. So this is a sampled distribution. And it's just me putting the observations from my sample into a histogram. And these are sample statistics because they come from the sample. So then, if I were to repeatedly take all of the samples of size 10 and calculate the sample mean for all of them and plot them, I would have my sampling distribution of X bar. So this is my sampling distribution of X bar. It's the distribution of the sampled statistic, or sample mean here, from repeated samples of size, here it's 10, from the population. And we can calculate, okay, the center here, it's going to be 50, just like it is in the population. And we can calculate the standard deviation for it as well. And then the note is the sampled distribution is usually the one we have access to. We dream of having access to the population distribution or the sampling distribution. It's less likely. It usually requires you to have access to the entire population. So here we have an example. They're still interested in looking at the average weight of a particular species of fish in that particular lake. So the researcher randomly samples 689 fish, and they plot the weights from those 689 fish in a histogram. So here they want us to say, okay, the histogram of the 689 fish represents the... So unless your population is just these 689 fish, it's not going to be your population distribution. And then you have to ask yourself, sampling means I'm going to have repeated samples. And it looks like we only took one. We took one large sample, or it's large to me. I don't know, I don't fish much. So this is our sampled distribution, because the histogram of the 689 fish weights comes from one sample. So same problem here. The researcher wants to repeatedly sample the lake this time. So this time they go out, they take a random sample of 689 fish, record their weights, probably put them back. Then they go out and they take a new random sample of 689 fish, record their weights, put them back. And they just do this repeatedly. They must have a lot of time on their hands, right? So if they go ahead and they take the sample average from each of these, and then they plot that into a distribution, we want to know, is this sampling distribution, population distribution, or sampled? So right off the bat, because they are repeatedly sampling and they're recording something each time they sample, this should lead me to, this is not just the sampling distribution, but it's the sampling distribution of X bar. So population, no, they're not recording all the fish at once. They are recording repeated samples of 689. And then sampled, that would be just one sample. They took many. So distribution of the sample mean. So we really like to be able to describe how that sampling distribution is shaped. And we know that, so the mean of the X bars is just going to be the mean of the population of all the individuals. So the standard deviation of X bar is the standard deviation of the population divided by the square root of your sample size. So your sample size does matter. So as n increases, your standard deviation of X bar decreases, right? Because as a number gets really, really big on the bottom, this whole number goes closer and closer to 0. So you start off, you want to know mu. So I'm going to take a random sample, calculate X bar, repeat, take another random sample, calculate another X bar, repeat. And then we're going to plot these, take some more random samples, get more X bars, plot them. And so now we know it's centered at mu. We know roughly how it's spread out. The central limit theorem has this really great feature though. So if our sample size is big enough, not only do we know where its mean and its standard deviation, we also know that the sampling distribution of X bar is roughly normal. So we now know how it's shaped, which means we can now use our Z table and our Z scores and whatnot to find probabilities here. So as long as n is big enough, then we can, the central limit theorem will kick in. And we're going to talk about what is big enough. So it must be sufficiently large. So in general, rule of thumb that we're going to use, at least in this class, we are going to usually say, hey, if our sample size is at least 30 and we're looking at means, we should be good. It should be big enough that the central limit theorem will kick in. Keep in mind, grain of salt, we're saying that 30 is close enough to infinity for us, for this to work. So it works in this context pretty well, but keep in mind, when was the last time you opened your bank account, saw $30 and went, yes, I can retire on this, right? So, grain of salt, 30 is close enough to infinity for this, but it's probably not for other things. So here, if I have a population, so my population is here, and I know that the population's normally distributed, any sample size will be big enough for the central limit theorem to kick in. So if I have a population and I know it's symmetric, but I know it's not normally distributed, I should take sample sizes of at least 12. And that will be big enough. So if I have a sample size of 12 and I know that the population is symmetric, that'll be, big enough for the central limit theorem to kick in so that the sampling distribution of X bar will be roughly normal. However, if you have really skewed distribution for the population, you're going to need a large sample size. So if it's really skewed or you have extreme outliers, you're going to want to take a sample of at least 30. In general, 30 is going to work pretty well for us. And then there's one last, we're going to go into this some more. This is week 10. So there's a rule about how big the sample size has to be there. We're not going to focus on this yet. That's week 10. So some examples of sampling distributions in the central limit theorem at work. So if I start with a normal population and I want to take samples from it, there's no sample size condition. Any sample size will work. That my sampling distribution will be normal. So here we just were being convenient. This is actually a standard normal. So it has a population mean of 0 and a standard deviation of 1. So if I take a sample size of 3, my sampling distribution is pretty normal. If I take 30, pretty normal. 100, pretty normal. And you can see that the bigger my sample size gets, the narrower the distribution gets. And then if I have a population that isn't normally shaped, you're going to need to have something that's usually at least 30. So here I have a really skewed distribution. If I take random samples of 3, the central limit theorem doesn't kick in. My sampling distribution has this like weird shape. It's really long tail. It's not normal enough. If I take sample sizes of 30, this is roughly normal. Well, if I could draw it accurately, right? And then 100, this looks really great. It's really narrow. It's harder to draw around here, but yeah, as long as it's at least 30, except for week 10 stuff, which we'll cover, it's going to be a big enough sample size for the central limit theorem to kick in. So finding probabilities. So this is handy here. So we were looking all at the normal distribution last week, and when central limit theorem kicks in, we can use z methods. So if we know that the sampling distribution of x bar has a normal distribution, we can convert x bar into a z-score and then use a z-table to find a probability. So here are a couple different ways. So you can write it as z is x bar, so whatever you observed in your sample, the mean in that sample, minus the mean, the overall mean, divided by the standard deviation of x bar. If you remember, this is equal to this. So either way you calculate it, these are the same. And definitely here we have a legend. So that's it for lesson 20. And then we're going to start practicing using the central limit theorem in example problems.